Okay, let's get started. I'll join everybody else in saying my thanks to the organizers for putting this together, this really interesting workshop. One point for the people in the back of the room, can you see down here?
No.
I can't do anything about that. I know that at various points in the talk, interesting things appear here, and sometimes there's an equation that appears here. So you either have to stand up or twist your head or something. Right now, what you'll see down here is a long list of names. These are all various collaborators that I've worked with in the past year, or I am working with. And they really shaped my thinking on holographic complexity. But in this progress report, I'm actually going to focus on one project with a fellow called Roe Jefferson. And so I apologize to the rest of my collaborators for not mentioning our papers together. The other thing is, although I've been privileged to have an extra 15 minutes, more than everybody else, I still think I have too many slides. And so the first thing I wanted to show you was the last slide, which down here again says that there's this really cool workshop happening in Perimeter in April, and I encourage you all to come. And I'd like to extend a special invitation to Dorit and Scott as representatives of the indigenous peoples. Very mutually beneficial cultural exchange, and so I encourage you to come. Okay, where does the story start? Well, it starts with Lenny here. Many of you know that I'm a big fan of entanglement entropy. But Lenny told me that entanglement entropy is not enough. When you're living on the other side of the continent across an international border, it's easy to ignore him. However, then we ended up in this It from Qubit collaboration. I end up going to workshops where I'm sitting in the same room. He sends me excited emails about their latest results. And so it's much harder to ignore these comments, and so in the past year or so I've been thinking about not just entanglement entropy, but now about holographic complexity. So what did those folks do? It's not just Lenny, but Lenny's team of collaborators, which again is in the bottom line, I'm sorry. What they did is they brought our attention, or they focused our attention to two interesting new observables in the ADS-CFT correspondence, and suggested that they would be related to complexity. And so Adam gave us a beautiful talk about this idea of complexity equals action and how that works. He also alluded to another possibility that complexity equals volume, where what I'm looking at is an extremal surface that extends across here from a time slice on the left boundary to a time slice on the right boundary. And by design, both of those observables are built to probe this region behind the horizon near the singularity.
And they're called observables because you can't observe them, right?
Yeah.
Aren't they properties? Isn't that what we learned after?
Okay. Can I say they're observables? And for Scott, I'm going to introduce this notation. When we put quotes on things, what that means is I'm using a carefully crafted set of words to engage with the audience in a positive way and move the discussion forward. I think in California those are now known as alternate facts. In Canada, we often refer to them as little fibs, although on occasion we may encounter the big fat lie, but that's my notation. I'm sorry I didn't put the quotes on the observables. In any event, I could give a very long talk in which, in various papers, we talk about various properties and details of these new observables. But how could I ever compete with Adam's animations? And so I'm just going to skip to the last slide, number 42. Where what you end up with at the end of that talk is a whole list of questions. In particular, I'd like to point out the questions at the top which I can paraphrase in the following way. What the heck is Lenny talking about in a language that Scott may relate to? The oracle gave me the answer, but I'm having this problem decoding it. So, in fact, what I'd like to focus on are the 2 questions in the box. And so most of the progress report is going to be steps towards trying to understand what complexity might mean in quantum field theory. Ultimately, though, the goal is to understand, well, whether this is actually the boundary dual of these new properties or observables in the bulk. And I'll have a little bit to say about that towards the end of the talk, but really not so much. So to begin, I should share with you my ignorance of complexity, and I'm going to give you a model. This is my understanding. This is what I'm going to be talking about when I talk about complexity. And it's really the quantum circuit model. So here we have our reference state, some simple state, perhaps all zeros. We're going to apply a unitary to produce our favorite target state over here. That unitary is going to be built out of some simple gates, some universal set of gates. And we put them together then to take us from our reference state to the desired target state. Now, if I'm using discrete gates, that can be really hard to do, and so we'll do it within some tolerance. And so that's a story that we've heard several times. And what I'm supposed to do is just count up the number of gates in the circuit that I've built here, and that minimal or the optimal circuit of the minimum number of gates then tells me what the complexity is. Now, one of the things that I want to emphasize is that I'm making a whole bunch of different choices here in preparing or coming up with this algorithm to calculate a number. And the answer that I get depends on the choices I made there. And that's something that I've just grown to embrace, and that's a part of the story. The question then is, given that collection of numbers, can I do something interesting, or does it inform me in some interesting way? But then, the challenge today is to try and take those ideas and apply them in quantum field theory. So here's a simple quantum field theory that I might want to think about. So I'm going to think about a scalar field in d space-time dimensions. Here I'm showing the Hamiltonian. So I'm integrating over a time slice, I'm integrating over the spatial directions. Here's my momentum term, a standard gradient term, and then I could have some interesting potential here. That potential still looks somewhat intimidating, and so I'm going to do this. I'm just going to think about a free scalar field theory. And since I'm in Princeton, or I'm not in Princeton, I'm in Stanford, I can expect the following reaction. What the heck are we ever going to learn about holographic complexity by studying free fields? After all, there's no black holes, there's no randomness, there's no Lyapunov exponents, and so I'm just going to put my cards on the table and say that in this talk I'm not going to try and answer any question which Lenny thinks is interesting. However, I want to try and lure the rest of the audience in. You can take a nap, that's fine, but I want to try and lure the rest of the audience in with the following hook. And I'll remind you about a connection between the idea on this side, the complexity equals volume, and something that often goes by the name ADS Mira. So Mira is this multi-scale entanglement renormalization ansatz. It's a way to represent the wave function of our favorite spin chain down here. And in particular, though, I draw this pretty picture, and the little blobs you can interpret as unitary matrices, and you can really think of this as a quantum circuit. Now, Brian, wherever Brian is, what he suggested is that this circuit is actually a discrete representation of a time slice in our ADS space. And so if I want to count the gates, then this is just the same as evaluating a volume of that time slice. Now, if we think, as we implicitly do, that this circuit here is somehow an optimal circuit or the most efficient way of preparing this state down here, then in fact what we're doing is we're evaluating the complexity and setting it equal to the geometric volume using this association here. And then I'll just remind you that there is an equivalent, or there is an ansatz, there is a description of the ground state of a free scalar field theory which uses very similar technology that goes by the name C-Mira or Continuum Mira that was developed by these folks here. My apologies to Tobias, I'll put you at the bottom of the slide again. And by the way, did I mention that we're running this workshop on continuum tensor? In any event, then, what you might hope to do in this study of complexity in this simple theory is you might hope to be able to capture some of this geometry. In fact, I won't quite get there, but I think we're well on our way. So let's see what we can learn. Well, given this free scalar field theory, the first thing I'm going to do is I'm going to introduce a cutoff. I'm going to put it on a lattice. Now the advantage there is that, well, I've reduced the problem to quantum mechanics, and what I have is a whole bunch of coupled harmonic oscillators. So that's a much simpler problem than the problem I set out with originally, but it's still rather intimidating that there's an infinite number of them. And so what I'm going to try and do is I'm going to reduce the number down to 2. I'm going to think about 2 coupled harmonic oscillators. That's a problem I think that I can deal with. It's a problem that everybody recognizes, and most of us can even solve it without referring to Wikipedia, and even if we can't, we can access Wikipedia. So what do we find on Wikipedia? Well, for this problem, the obvious thing to do is we look for the normal modes. And when we write it in terms of the normal modes, it just becomes 2 decoupled harmonic oscillators with slightly different frequencies. And so given uncoupled harmonic oscillators, we could start to write down wave functions. So for example, I could write down the ground state wave function, and it's just the wave function of each of the ground states of each of the normal modes. Here I've written it in terms of these normal modes, but I can then translate that very simply to a wave function on x1 and x2, the original variables in our problem. And so here's my ground state wave function, and I'm going to declare that's a pretty cool wave function. Let's make that our target for a simple, or our first simple approach to evaluating a complexity. So we have a target state. Another thing that we're supposed to pick in defining complexity is the reference state. And so what's an interesting reference state? Well, again, I'll just declare, here's an interesting reference state. It's just 2 decoupled Gaussians. Like you might think of this as being the ground state of the oscillators when I don't have the interconnection between the two. So if I throw away this interaction term, then these were originally just decoupled oscillators, and their ground state would have looked somewhat like this. I'm just going to, though, allow for any old Gaussian, so that omega naught is not a frequency in the problem, it's just one that I get to define, and we'll talk about that more later. And so this goes by various names. I can call it a factorized Gaussian. It's also a special case of a squeeze state. But that's what I'm going to declare to be my interesting reference state. So now what I need is gates, or unitaries, to act, and to get me from here to here. So, well, the natural operators in the game that I'm given are the positions and the corresponding momenta. So let's start building some unitaries out of those operators. This one's actually kind of trivial. What I have is an exponential, and up in the exponent, the x naught and the p naught are actually c numbers, so they're just placeholders, but they're going to reappear later down here. But the key thing is that I'm going to stick an epsilon in there. That epsilon is some infinitesimal parameter because I want my gates to make small changes to the wave function, and I'm going to make the changes gradually. And so this one, that's just a C number, and so what it's doing is it's adding a small phase to my wave function. I can proceed, now I can stick a real operator up here in the exponent, so here I've stuck a pi. And so what that's doing is when this acts on the wave function, it shifts the coordinate xi by a small amount. It shifts it by this epsilon x naught. Alternatively, I can stick an xi up there, and then I'm shifting the p, or because I'm working in position space, I'm just multiplying by a small plane wave component. Now things get more interesting when I have two operators up in the exponent, and they're really two different classes. The first one, these exponents, or these operators have different indices. And so what that's doing is it's shifting xj by an amount proportional to epsilon and an xi, which was one of the other operators. So that could be 1, 2, or 2, 1. Alternatively, what I can do, they can have the same exponent, then I have to play a little game to make sure that it's really a unitary operator. And at the end of the day, I can write it like this. Essentially what I'm doing is I'm shifting xi by something proportional to xi, and so that's like scaling, or I'm rescaling that coordinate. And so these are going to be the key players in the game, and they essentially do two things. The first set of operators entangle the two masses, and then I can think of these as scaling operators. Now, I could keep going, and I could stick, for instance, I haven't even thought about things like x squared, p squared. I could put x cubed p. I could keep going, but I'm just going to stop here for now because I know that's enough to get me from here up to here. And so these are going to be the gates, or the only gates that I need in the problem that I'm studying. So here's my reference state, my target state again. How do I build a circuit? Well, a circuit consists of just applying these gates one after another, and so here's a simple way to get from the reference state to the target state. First, what I'll do is I'll scale up x1, I'll scale up the prefactor here from omega naught, omega 1, and so I'll have to figure out how many times I apply that. Then I want to introduce some entanglement. I want to introduce that beta term, and so I figure out how many times I do the Q12, and then I fix it up by doing the final scaling on x2 to get it into that form in the top line. And it's a straightforward calculation, but the question I'm going to ask is, what are these exponents? And that's the cost. Or I use the word here, circuit depth, to distinguish it from the complexity. This is just a possible circuit. I don't have any reason to think that it's the optimal circuit. And so I don't want to call this the complexity, but rather I call it the circuit depth. And if you do the calculation, you get an answer that looks like this. And in general, what you'll get is some kind of expansion in epsilon. There'll be a 1 over epsilon term to start. And then there's an order 1 term, and an order epsilon, et cetera, et cetera. But basically what we can do is we can focus our attention on that coefficient of 1 over epsilon, and we want to try and figure out how to make it as small as possible by choosing the circuit in an optimal way or by applying these gates. But how am I going to find that optimal circuit? Well, we can think about what would that optimal circuit look like, or what's a framework where I could start to ask that question. And so here's a framework. I've got my, I've got a whole set of circuits here, but they're, again, acting on the reference state, taking me to the target. What I've done here is I've got all of these are the operators that were appearing in the exponents. I've ditch the epsilon, but essentially what's happened is I've replaced a bunch of epsilons with delta s's and turned it into an integral here. And then these are like the alphas. I'm going to turn the circuits off and on, or I'm going to turn the gates off and on. And so I'm going to indicate that by these functions as I move through S, or this parameter, which I let run from 0 to 1. I'm going to ask how many times do I have to turn on and off the various operators. And then the the path ordering, sorry. This is a path ordered integral. Again, the first delta S acts, then the second, then the third, and so we're building up the circuit from the left to the right. But I want to optimize that, and so I'm going to ask that the absolute value, or the sum of the absolute values integrated over S should be minimized. So I want to minimize this cost function, or this circuit depth, and that's equivalent to this sum over alphas that I had in the discrete case. This is sort of just a continuum version of that picture. So this is a framework where you might hope to find the optimal way to apply the gates and get the desired targets.
So in this continuum version, it seems like you'd have the freedom to pick a different coefficient of how much you're weighting each kind of gate.
Yeah.
Is there a natural way to match them up?
Why don't you wait one slide? Maybe two, I don't know. But then, so this is a framework where we can work, but where are we really going to find the right technology to do the job? This is again where I pay attention to Lenny. He's been telling me for 2 or 3 years now to go read the papers of Mike Nilsson, so I finally did. They're these very interesting papers. And so I'll just pull a few little highlights out of them. I mean, what Mike was interested in is this problem up here. What's the minimal size of a quantum circuit required to exactly implement a certain unitary operation U without the use of epsilon? The first thing he says is, well, we have to really, the best way to, or a good way to approach the problem is rather than thinking in terms of these discrete gates, I want to think in terms of a continuum. Smooth functions on a smooth space. I've already bought into that, and so I'm on my way. But then what else? Well, he says, I want to minimize this cost function, but I can think of that sort of as a physics problem. I can think of it as the motion of a particle governed by an action, and what I want to do is extremize my action. And one of the key things here that he did is rather than just thinking about the circuits, he thinks about trajectories on how I get from, or how I move through this space of unitaries, or this space of circuits. So rather than having 0 to 1 here, I let this run from 0 to S, and now I have a U that's a function of where I am along the trajectory. My initial condition is that I start with 1, and then I'm going to end wherever I wanted to end. This is going to be the unitary of the circuit that achieved this, the transformation from my reference state out to the final state. And again, he says, here is a possibility. This is a possible cost function that I might consider. And he goes on to talk about it some more. In particular, these y's you can think of as components of tangent vectors, of a tangent vector to my trajectories. And that the extremal path here is a geodesic. But it's a little bit unusual geodesic, or it's a little bit unusual geometry, and then it's something called Finsler geometry.
That's because you used the one norm.
That's because I used the 1 delta norm, actually, because this isn't a Finsler, but that's a detail. But as Aaron and Lenny pointed out, this is really attached to that, the choice of the cost function. And because I don't have time to tell you what, or I'm too lazy, or whatever. I'm going to change the rules of the game, and I'm going to choose this cost function instead. And now, if that's a velocity, this looks like a standard reparametrizable particle motion. And now I'm just working with a standard Riemannian geometry. And so we're going to study a problem that we're more familiar with. And in the language of Mike, what I'm doing is I'm going from the F1 to the F2 norms. Yeah, and in fact, you were asking about penalty functions, so I don't have to count all the directions the same. I can change the weight that I assign to different directions, and that just introduces a more interesting metric use. Rather than just adding up the sums of the squares, I can weight them differently.
Possibly get some interesting metric from like the Fisher information metric or some construction like that.
I'm going to show you lots of metrics, and none of them I think are the Fisher information metric, but I defer to the official answer is I don't know. Okay, so these are the rules of the game now, and I just wanted to fill in this this bit about this being a tangent vector. And I don't know why I thought that was so important, but I took a couple steps to do it. I mean, I've got my U of S, that's describing this trajectory. I take a derivative with respect to S. That's this last point, and so that's the furthermost to the left. And so it brings down the exponent sitting out there. Now you just multiply by U inverse. If these are nicely normalized generators, then I just multiply by M and I take a trace, and that takes out the components yi. And so it's in that sense that what I have here is the tangent vector to the trajectory described by U of S. And if I want, I can take that formula and plug it in up here, and I get a big long mass that looks like that. But the name of the game then is to try and, well, I've got a particular initial point, a final point, and I want to find trajectories that take me from one to the other.
Did you really get to take the square root, or could you use the quadratic average?
That's a really interesting point, and I didn't have to take the square root, but I insist on doing it because it fails at a certain point. Oh. So let's see. How are we going to apply this technology? Again, Mike was interested in a very particular problem of unitaries and qubits, and I'm not interested in that exact problem. Rather, yeah.
I'm going to ask, how do you pick the final unitary? Don't you just know like one biggest element of that unitary?
No. Wait.
Okay.
There is an ambiguity though. Oh.
S was a parameter along the circuit, which is
Right, so originally I started with this description here, and I had a parameter that said that I start at 0 and I end at 1, but what Mike told me to do is think about that whole trajectory. And so rather than integrating from 0 to 1, I'm just going to integrate up to an arbitrary S, and then I have a U of S. The one that I'm interested in, though, is the final, where I am at the end point. And the other thing I did that flashed when I changed is I had this cost function that was the absolute values, and now I'm using this sum of squares, square root. And then I'm told I'm supposed to evaluate the y's by using this formula here. Now Mike was doing a problem with matrices, and so it's easy to understand what that means. My m's are actually these operators, and so it's a little bit more difficult to understand what that means. And I'm not saying that it's impossible, but I'm not going to do that. I'm going to change my perspective. And so the perspective is that at this point in the game, in these first steps, all I'm thinking about are Gaussian states. And so rather than thinking about these wave functions themselves, what I want to do is I want to think of the space of states as being the space of positive quadratic forms, of being these coefficients, these matrices that appear up here in the exponential. So here's a particular state now. It's a particular matrix. I'm going to have a reference state that was just a diagonal matrix, and I'm going to take it to some more interesting target state. In that language now, I can translate all of my gates that acted on wave functions into matrices that act on, well, these quadratic forms. And so it's just a little bit of work to show that the well, these were my operators, but the corresponding matrix generators in this representation are just these matrices where I have a 1 in one place and a 0 in all the other places. And when they act here, they act in this quadratic way, or by the similarity transformation on A. Oh, and yeah, this is just to point out that the game has changed a little bit. I'm not working in the unitary group anymore. In particular, we're going to be working in the GL2 here, general linear transformations. And now it's going to be straightforward to evaluate this expression working in this representation, and so we can just take it and run. One thing I'm going to do just to simplify the problem is I'm going to get rid of omega naught for now. I'm just going to take the target or the reference state as being the identity matrix, and that just simplifies some of the equations. Omega naught will come back at the end of the talk if I get there. One comment is that I set up the notation and the formalism so that it generalizes very quickly to an arbitrary number of coupled oscillators just by letting the indices run over a bigger range. And so for n oscillators, instead of GL2, I'm working with GLN. I can also incorporate the C number bits here by adding special operators that do C number shifts, and that's also easy to do. This comes to Brian's question.
Great.
There's a mismatch in the parameters. My GL2 is a 4-dimensional space, 4 generators. My space of states is actually 3-dimensional because I'm thinking about symmetric matrices. And so there's a mismatch here. There's not going to be a unique solution to this equation, but it's really, there's a 1-parameter family of solutions. That's okay. All we have to do is find all of those solutions and then find the geodesic that gives us the minimal action or the minimal length. And so that's just a riffle, or it's a small change from the original game. So let's carry forward. Okay, we're looking for this right invariant geometry on GL2. I can think of that as R, the scale, times SL2. And let's focus on the SL2. If I take an SL2 matrix, I can write it, it's just a 2x2 matrix. In this way, I want it to have unit norm or unit determinant. And if I take the determinant, it looks like that. That's something that the string theorists all recognize because that's ADS3. So there's an interesting geometry. And so what I did is, or what we were motivated to do is, given our experience with ADS3, that helped us choose coordinates. In particular, we chose what you might know as global coordinates on ADS3. Rho is the radius, theta really is the angle, and tau is the time. The only thing that happened here, though, or the extra thing that happened is that wasn't the whole thing. I wanted to go to GL. And so I'm going to parameterize the determinant by that y, or the exponential of y, and so there's an extra factor here in front of all of the x's. And so if I plug that in, this is a representation of a general matrix, or a general circuit, if you like, in this particular problem.
Well, you somehow have to make it a curved space.
No. Wait,
ADS3.
it's down here. Wait. I promise. What we're going to do is we're going to think about these parameters as being, I'm going to trace out some trajectory in this space. And if I want the line element, what I was told to do is there's a specific prescription to identify the y's. And I'm multiplying by this ds squared, which is just to say that if I evaluate this, I get dots, and I want to get rid of the derivative and turn it into differentials. But I can just do that now. I can plug it in there, and then this is the metric that I get. And that's not AES3. And in fact, that's a good thing, because if we stared at this, this is Lorentzian AES3. And I don't want to have costs being negative. I don't want to. And so it was because I chose by construction, I built the Euclidean metric. My costs are all positive, and unfortunately it's not AES3, it's not the group invariant metric. The group invariant metric you get in the right basis. What you do is you stick omega ij in there, and that gets you this, or the standard metric. But that's not the metric that we're interested in. So what am I supposed to do? I'm supposed to find all the trajectories now that take me from my initial state to my final state. What is that final state? Well, I want to solve this equation here. I can just stick in, my u's in the coordinates that I gave you, and I evaluate that expression, and then I'm supposed to set it equal. And so I get these three equations. Omega 1 is equal to that combination 2 and beta, and there are three equations for 4 unknowns. One of the things is that if you stare at that, you see that the difference here between these, the angle and the time, doesn't appear anywhere, and so it's not fixed. So I'm going to have a whole family of circuits, but only one of them is going to be the optimal. And you might think of going to coordinates that are theta plus tau, theta minus tau, and that indeed cleans up the metric a little bit, but you really don't gain anything, and it makes other parts of the problem harder, so I'm going to ignore that. And so now you have to solve, and there's lots of interesting geometry you can't actually solve, but instead I'm not going to bore you with any of that. I'm just going to give you a picture. And so what I have in the picture is my space of circuits. It's labeled by tau on the vertical axis. I've suppressed y because I can only draw 3 dimensions. And then in the xy plane down here, I've got the radius and the angle. The initial condition is that I'm supposed to start at the origin, and then I'm supposed to go to the target, but the target had this freedom that only tau plus theta was fixed. The difference wasn't. And so I want to find the geodesics that land somewhere on this spiral that twists up through this space. So there's some geodesics. But then given that family of geodesics, I want to find the optimal one. I want to find the shortest one. And if this was actually 3-dimensional Cartesian space, it's relatively obvious to see where the shortest geodesic is. It's the one that takes me from the origin straight across to where the oval, or where the spiral pierces through the tau equals 0 line. And in fact, that is, in fact, the minimal geodesic. That's the one that tells us what the optimal circuit is. The geometry is a little more complicated, and you have to do some more math, but that's the answer at the end of the day. So it's a simple tau. We never get out of the tau plane. Theta is just a particular angle, and then the other parameters are growing linearly. And so this is the circuit that we get. It looks kind of like this. And you can evaluate the complexity, which is the minimal circuit depth, and it's just some simple expression like this, where I've got the rho 1 squared and the y 1 squared. And I can remind you that those are parameters that, implicitly are defined in terms of the data I gave you, these omegas and the betas. And so in principle, you could unpack that and turn this into an expression of omegas and betas. But I'll tell you that that's really not worth it, because I actually solved a problem that was a little bit harder than we had to solve. If we go back to the original problem that I wanted to solve, it was this one. Here's my target state, but in particular, these two frequencies, omega 1 and omega 2, are equal. And that's just the translation invariance of the problem. And another property is that beta, the off-diagonal one, for this particular case, happens to be negative, because omega minus is bigger than omega plus. And so let's solve that problem more explicitly. you know, the thing that changed here was my target state. That means that when I wrote down these equations, there's no independent omega 2 here, rather it's omega 1 and omega 1. If you stare at that, you better make the sign disappear so that these two expressions are equal. So you could think that I'm going to set those equal to 0, but if we remember that beta is negative, then I actually want the cosine to be -1, and so I'd rather set that sum to pi. Nothing else in the problem changes.
Question.
Yeah.
Yeah, so, I mean, the optimal trajectory you get, how does it relate to somehow turn on the Hamiltonian adiabatically?
Sorry, you said?
Does it somehow relate to turn on the Hamiltonian adiabatically in a certain way, or?
It might, but I'm going to say no. The remarkable thing is there's no physics here. Physics told me that, you know, what an interesting state might be, but the rest of it is just a set of rules, some software that I wrote to evaluate the complexity. But it's really not a physics problem.
But then if you restrict yourself to just turn on Hamiltonian adiabatically, analytically in a certain way, you have different ways to turn it on. What kind of improvements does this give you in terms of the depth of the circuit?
What I'm telling you is that what I'm doing is for my software, I ran and I got an answer, and that is the optimal circuit. And it really isn't a physics problem. It's just this set of rules. Why don't you ask me later? I can tell you're still unhappy. Sorry. So we plug that in there. We set this equal to pi. That simplifies some of these expressions. The only thing that happens in the picture now is that the place where it cuts through the tau equals 0 plane is on the negative axis here. Theta is equal to pi. But everything else is more or less the same, except I chose a pi there. That simplified this matrix. And the complexity is this. But now I can think about unpacking it. The best way to unpack it, though, is in terms of the normal mode frequencies. And you see that there's a very simple expression. Log squared of 1, normal mode frequency, log squared of the other normal mode frequency, square rooted. And so that, again, using my software, that's what the output is. This is the complexity of the ground state of that couple pair of
So how does it depend on omega 1?
That's because I threw omega naught out.
Okay.
I set it to 1, so all of these are actually ratios of the normal mode frequency over the... What else could we do? Well, there was this idea of adding penalty factors, or weighting different directions in different ways. And in particular, one interesting thing that we can already do is we can think about weighting the entangling directions differently from the scaling directions. And so if you remember the operators I wrote down, I said that there were these two classes, one where we were, you know, tying one x to another, and one where we were just scaling one of the x's. So you might think that it's interesting to weight these generators differently than those generators. You can actually see that in the n-oscillator case, or for a chain or a lattice. I want my software to preserve some notion of locality in the chain or in the lattice. And so my expectation is that I should come up with rules that punish me if I'm trying to entangle masses or degrees of freedom that are widely separated on the lattice. And you can actually see that in the discrete case. These were my gates they involve 3 different masses that I assume are nearest neighbors. All of these gates only involve next to nearest neighbors, but what it produces in this combination is a gate that involves skipping one. And so each one of these produces a shift of order epsilon x. What this is doing is it's producing a shift of order epsilon squared x. And so you might think, this is a harder thing to do than next to nearest neighbors. And so all I'm going to do in this simple examine that story is to stick in an extra factor here to weight the use of these generators more than the weight the scaling generators with the scaling direction.
So A is bigger than 1.
Yeah, A is bigger than 1. You can think of it as being really big if you want. And the story is the geometry's much more complicated, but essentially I get the same minimal geodesic. You know, here's the geometry that you're working with, but the minimal geodesic is still this straight line that runs across in the XY plane. The circuit still looks the same, and the complexity changed because these off-diagonal terms are weighted by that penalty factor. You can again try and unpack that in terms of the parameters of my original problem, the coupled harmonic oscillators. And so there are expressions here with omegas, or omega, the normal mode frequencies. You can rearrange it to look like that. It's a little bit shorter. It's not much more enlightening, but here's the A squared term. It's got a ratio. And then there's this order 1 term, which has got the product. And there'll be omega naughts in there. What else can we do? Well, I kept saying that the normal modes, the answers looked really simple in the normal mode basis, or in the normal mode picture. So maybe we can just study this whole problem in that basis. Remember, that's the first thing we did when we were solving the coupled harmonic oscillators. We went to the normal modes, et cetera, et cetera. I'm just going to establish some notation with that set of equations here. Anything with a tilde is in the normal mode basis. Anything without a tilde is in the original physical basis. And so it's just a rotation to go from dx1, x2 to dx plus and minus. And here's the rotation matrix. I can start applying that rotation matrix all over the place. In particular, I can apply it to the target state, and it diagonalizes it. Of course, that's what it was supposed to do. The reference state was just the identity, and so it didn't do anything there. But I can also now try, I can start to think about what does it do when I apply it to the generators and to the circuit. And this is the picture that you get in the normal mode basis. This was our optimal circuit. And now we can understand why it was the optimal circuit. In the normal mode basis, I really had these two coupled oscillators. And so I had these two separate unentangled Gaussians. And all I'm doing here is I'm pumping up the frequencies to get to the appropriate normal mode frequencies from whatever my reference frequency. Well, here the reference frequency is 1. And so you can stick those in. But, we had a reference state that was in the diagonal. We have a target state that's in the diagonal. So you could wander off into the geometry, but that's, well, intuitively, that's just more complicated. And so the minimal circuit is the one that's just traveling along, and it keeps us at every stage in the diagonal. So we go from one diagonal state to another. I can also, just to build on that a little bit more, I can think of my original circuit, but write it in this basis, where these are now that I can think of those as the generators for pumping up the normal modes. So there's a plus plus, which is some linear combination like that, and a minus minus, and I just flip some of the signs. But the point is that these two generators, although they look complicated in the position space basis, I know that they commute. And so what that means is that if I'm focusing my attention on the normal mode subspace, if I'm only ever traveling through these diagonal states, then I'm going to see a very simple geometry because they commute. In fact, that subspace is flat. So that's this bit over here, that's the thing that's changing, that's where my trajectory lives. But I can actually write it in terms of these coordinates, and you see, these are precisely the normal mode coordinates or another coordinate, and you see that you're getting flat. But that's always, again, that's a general lesson that's going to extend to the lattice. I'm going to have a bunch of well, the easiest route is just going to go through this normal mode subspace, and the generators are always going to commute. And so unfortunately, I'm going to end up with a flat geometry. I mean, I have a very complicated geometry, but the part of interest is just this flat bit.
But that presumably has to do with the fact that it's a free field.
No, I don't think so, but why don't we say that? It's that and the software that I wrote.
Yeah.
The one thing I want to remind you is, although I made this seem, or now we see that it's a very simple problem in this particular basis, when I want to introduce these penalty factors, that's something, again, that refers to locality. That's something that refers, or is going to make sense in the position space. And so we don't want to just jump over into the normal mode space and forget about everything else, because that's going to be the interesting, or it's going to be some of the interesting physics. Okay, so having learned as much as we can from the case of two coupled harmonic oscillators, I want to go to a lattice now. Well, what I wrote is n to the d. So I'm going to have a periodic lattice that's n sites this way, n sites this way, n sites that way. So it's some kind of cube like that. And I'm not quite going to go to the main event right away. For simplicity, just to gain some intuition, I'm going to think about the case where those oscillators, in fact, aren't entangled. And you might think of this as giving me a lower bound on the complexity. Because, you know, I'm going to start with my reference state. I'm going to pump up to sort of the zero mode, or the ground state of the uncoupled oscillators, and then you're going to add some entanglement on top of that. But then there is a warning that's in quotes. So unfortunately, it's not quite true, but let's try it out anyway. Let's see what we get. Well, my claim is that, you know, I'm just going to go, and then for each one of those oscillators, I'm going to get a factor like this. I'm going to square it, I'm going to add them up, and then I'm going to take a square root. Or actually, well, that half started its life as 1/2 log n. And so the answer is going to look like this. There's going to be some factor involving n, and then there's this factor that's common to each one of the oscillators. And that's interesting, because this is where I think you see that it fails. Or at least it's not what holography does. This is actually the volume divided by the cutoff to the appropriate power, but then there's this extra factor of 1/2. What we know from holography is, well, by doing lots of calculations, you see that the leading term there is actually proportional to the volume divided by the cutoff. And so this is an annoying square root that appears here in our calculation. But we can see exactly where that square root came from. It was the square root that we put into our cost function. And so it suggests then that if I want to emulate holography, I should discard that set of cost functions, and I should work with some other set. In particular, there were these cost functions where it was linear in the y. But in fact, all we're dealing with, all that was really important here was a sum. And so you could get the same answer from any one of a number of different cost functions. In particular, there's Lenny's favorite here, where I'm squaring things, or I could take cubes, fourths, whatever. The key thing is I don't want to do that square root, which is unfortunate, but that's how we can make contact with the line. Another thing that we might, where? Douglas.
So, well, this is partly a question for you and partly for Adam and Lenny. So, I think in one of their most recent papers, they put a factor of the square root of the number of degrees of freedom multiplying the distance in the Nielsen measure as their complexity. my impression was that that square root was supposed to fix this square root. Is that, maybe,
I think so.
so you guys say the complexity, the Nielsen complexity is supposed to be the distance in Nielsen geometry times the square root of the number of degrees of freedom?
Which I think translates to an action. An action, a quadratic action.
So you say that's the same thing as
I
taking
think so,
this?
I think so. I think so.
But
Well,
maybe
what
we could
I-
fix Rob's formula by just putting a square root into the d minus 1 in front and using this.
You could start dabbling and sticking all sorts of factors. I prefer not to. I mean, this is a natural fix. This is actually the most natural choice for the penalty. That's the one that connects most closely with.
It's just not a very nice geometry that you get that way, right?
That's a matter of perspective, isn't it? We like Riemannian geometry.
This, right.
Maybe that's
In other
the.
words, this is what you need to do to make the complexity extensive.
Yeah.
If you want it to be geodesic length.
Yeah.
Yeah, I think we have, okay.
Well, okay, we can talk about it later, but, well, here's a whole raft of things. Another way you can do it is, well, I don't like my answer, I'll just multiply by the volume to the 1/2.
So do we not need a reparameterization symmetry of this integral?
Nope.
No, because I would have thought if you were going from one point of this space to another, that shouldn't matter how I parameterize that curve, it should only matter the path length. And it seems like some integrals will have that property.
Yeah, it is, but, well, okay, I'm almost at the end, so I'm just gonna say no, and you can grab me at lunch. The other comment I wanted to make, or the other observation is, there are logs here, which is actually kind of interesting. Why is it interesting? Well, this was slide 38 of the talk that I didn't give. And what you can see in complexity equals volume is here's my power, and this is going to give me a volume. But when I go to complexity equals action, here's my power, and this is going to give me volume. But then if I wander over here, there was this extra log term within log of delta. And that came from a certain place, but the fact that it's adorned on my transparency in this way means that we were confused about what that contribution is really doing there. But here we have an answer. We see that naturally logs are coming out of the story. When I wrote it this way, I made the assumption that omega naught, that was my reference frequency, was much bigger than the mass, the infrared scale of the problem. But we might think a little more carefully about what omega naught to choose here. One possibility is I want to put it way up in the ultraviolet. I want to put it at the cutoff scale. And so my Gaussians are all narrowly focused. And then what I would be getting out of this term is an extra log factor that involves the cutoff, because that's where the problem started. On the other hand, I could pick some other scale that's down in the infrared. I had a mental block when preparing the transparency, and so I insisted that it was bigger than M, but less than the cutoff. In principle, you could let lambda wander off into the infrared. It could be the size of the volume if you wanted, or inverse to the volume, but this is one particular choice. Inevitably, what you end up with then are ratios of two infrared scales. One is a physical scale, and one is just a scale in the problem that you got to pick. Seeing that, you can run off and start to make all sorts of extrapolations and speculations. Well, let's not do that just yet, because we're here just looking at this crappy practice problem. What we really should do is look at the full problem, where I'm going to restore the coupling between the oscillators as well as the mass. And so in that case, again, my assumption is that I'm going to state without, I'm going to assert without any justification, we're going to be traveling through the normal mode subspace. I'm always going to pick up factors like this, where what I'm doing is I'm pumping up each of the normal modes from some reference frequency to the frequency that our target frequency. I've just let the measure be whatever it is with powers, Lenny wants alpha to be 2, but I'm letting it be something else, very arbitrary. And the spectrum on my d minus 1 dimensional lattice looks like this, with an m squared and then a momentum. One of the things to note in trying to interpret that answer is that most of the modes are in the UV. That's the usual story. Most of the modes are out at high momentum or short wavelength. But what that means here is that most of the modes have frequencies proportional to 1 over delta. And so that's going to let us make an approximation and pick out the leading term, but I still have to choose my omega naught. I suggested 2 different ways. One way was some infrared scale, which may or may not satisfy that inequality. It may even be further in the infrared. In that particular case, I get something that looks like this, where again, I've got my desired volume term because the sum wasn't under any square roots or anything. And I've got some power of a log that involves an infrared scale and the cutoff. Here again, if I wanted to emulate holography, that would suggest that I want to pick a particular power here, because I did see terms like that in the divergent structure of complexity equals action, but it wasn't higher powers of that. And then there are subleading terms that actually also appear without the law. Okay. What would you like me to do? I could quit here.
There's a maintenance.
Okay, I'll go faster. We can also set the reference scale out in the ultraviolet. In that case, there's no log, and so there's something interesting going on. And I'd like to talk more about that, but I don't have time. I'll just mention in passing that you do get subleading terms that involve the mass squared, so that might also be a useful way to probe various parameters appearing in your measure. Then there was the question of penalty factors. That's a work in progress. Where's the geometry? Well, all I gave you was a flat geometry. What we really want is to do something more creative. We want to improve on our software. That's a work in progress as well. And then I'll just remind you that there's an interesting workshop. I'm sure that if you come to that workshop, I'll tell you where the geometry is by that time in a month from now. So there I'll stop.